I've got Zoom things on there. So what I'm going to be talking to you about today is time. Now, logically, being a clock club, it seems logical that we would be talking about time. But if you're a nerd like me, there are some other things that might be of interest with regards to clock club and time. Let's see if I can
Don, just before you start, I know we've got at least 2 Toronto chapter members, Ben Orsolak and Graham Jones, on our screens as well. So I don't know how many we've got people coming from other chapters, but welcome.
Excellent, welcome. And maybe if we could record that, that'd be great. So some of my interests. When I joined the Clock Club many years ago, I was interested in a number of things. You know, people are interested in collecting. There's a certain number of clocks I'm interested in collecting. I was definitely interested in repairing, and then also interested in understanding the mechanical relationships of clocks. And that's something that has always been a key driver. I always wanted to understand how they work and why they work, and the gear ratios. Another thing I'm interested in is astronomy and space and time. And I know a lot of you, just like me, when you go to bed at night, you try to think about infinity. And how can infinity really exist? And what is infinity? And how about the Big Bang? And you can sort of see on the left-hand side of this top left here, the word Big Bang. And this is a visual representation of the Big Bang when the universe started very far at the end here. And then it rapidly expanded. And it shows you here space, time, and all the universes and galaxies and stuff expanding over time. So obviously this is something I know that you think about when you're going to sleep, just like I do. And of course, there's my big guy here, Einstein, and his theory of relativity. But this is stuff that I always just find very interesting. So, do horological issues and relativity issues make a good match? Well, the answer is yes. And the purpose of this slide is to demonstrate why. So you can see the Starship Enterprise sitting there just ready to do its thing. So what's the issue? Why would I even want to write a presentation on this topic? And I don't know if any of you know, but if you go to the CN Tower, on the bottom, your wristwatch is running at 1 speed, but when you take that elevator up to the tippy top of that CN Tower, your watch actually speeds up. And it's not just your watch, time itself actually speeds up. They've taken atomic clocks and they've tested it, and it's measurable. Of course, it's not big, but because the distance isn't that far, but your time actually runs faster at the top of the CN Tower than it does down at the bottom on ground. And this is known, excuse me, this is known as gravitational time dilation. So you'll have to remember that word. So that's a real effect. It's measured and it actually does work. So let's take that a little bit further. What happens if you live up at the International Space Station? And especially there's this one guy, excuse me, I think he was a Russian who was up there just recently for a year. So what effects has he had on with regard to all that? Well, the astronauts are 260 miles above the Earth, so that's a big difference from the CN Tower. So, coincidentally, their time will be running faster than our time. They age faster than we do, or they should. That's why I said there should in quotes. So, following the logic that we had with the CN Tower, their time runs faster, measurably faster, and actually they do have a correcting device so that they can correct the time differences between the two. But how can this be? And the answer would be gravity. Now, if anybody has taken any physics, higher level physics, you will know that the effect of gravity on time space it warps it. Now, in the diagram to the left here, you can see the Earth, and this net effect is just to show you, to demonstrate how gravity, the gravity of the Earth, warps time space. Now, if you've ever gone to a grocery store, they used to have these things where you have a quarter or a nickel or a dime, and you put it in this big, huge plastic bubble, and then it runs around in circles and circles and circles and circles until it finally falls down the hole in the center. Well, that's exactly what this is doing too. So if you had a satellite, the satellite stays in orbit because of that warping of time-space due to gravity. If you had a bowling ball and you rolled it across that time-space thing, if it was far enough away, it wouldn't be sucked into that dint in time-space. But if it was too close, it would start circling around the Earth, the time-space, and then finally fall into the Earth because of that warping of time-space. Cool. So this is another example of how it would look. The Earth is sitting there, and time-space is warped, and then the Moon, for example, is orbiting the Earth same way as that nickel dime quarter orbits that hole in the center of that thing in the shopping center. It orbits the Earth because of that warp in time. Now, if light passes through there, you can actually measure the effect of that kind of a ripple with the bending of light around a planet. So you can actually see light bend around past planets. So that's one way that they measure this and show that it actually works. So this is the same sort of thing that if you had a bowling ball and you stuck it on your bed. The bowling ball would have a dent in your bed, and then that's the same sort of effect. But wait, that's not all. So time-space gets warped, but there's something else called the relative velocity time dilation. Lots of big words, but just think of the picture here. If you're standing on the road and a train goes by beside the road, going, that's the Doppler effect. Well, that's the same sort of effect that happens with time when you speed up towards the speed of light. On the right-hand side there, you see the Starship Enterprise going into warp speed. They never talk to you about the results of or the effects of going into warp speed, but they should, because they always come back to their space station, or they always come back to Earth, or wherever they're coming back to, and everything stays the same, but it shouldn't. So there's an error in Star Trek. So the faster you move towards the speed of light, time slows down. Time slows down the faster you travel. And so you age more slowly the faster you move towards the speed of light. So that means that the effect on our astronauts, remember the astronauts are circling around the Earth? The astronauts, they're circling around the Earth at a speed, at something like 5 kilometers per second. And so, because of that, the effect of their traveling around the Earth is somebody should turn off their microphone, because I can hear myself talking, so make sure you mute yourself. The effect of traveling around the Earth is that time slows down for them relative to us on Earth. So that's because they're moving faster than we are. We're stuck on Earth, but they're moving 5 miles per second around Earth. So time slows down for them. So we talked about two things for those poor astronauts up there. Because they're further away from the Earth, time speeds up. But because they're traveling faster than we are, time slows down. So the actual overall effect of the two of them is that the slowing down is bigger than the speeding up, and they're aging a bit more slowly than we are. So there are two effects working on them. And the effect of the two is that overall time is slowing down for them. So that Russian astronaut who went up to the space station for a year will be coming back from the space station a little bit younger than his family would expect him to be. So why would I even want to talk about this? How does this affect us? Well, I don't know if you've been listening to the news lately. This kind of thing drives me nuts, but there you go. Humanity plans to set up outposts on the moon. China, Russia, India, North Korea, everybody wants to set up outposts on the moon. Why? I don't know, but they do. But what's the effect of that? Well, if they're living on the moon, the gravity on the moon is less than ours. Their gravity is 1.62 meters per second square, less than Earth, which is 9.87 meters per square. So it's like 1/8, or almost like 1/9 our gravity. For them, their Pagnot clocks will be running slower on Earth than on Earth. So their time will be running slower than our time. So go figure, somebody living on the moon, our time is different than their time. And I'm not talking just the running of a clock, I'm talking about real time. Similarly, they've been talking about going to Mars. Well, its gravity is 3.711 meters per second squared. So their clocks will run faster than the moon, but slower than Earth. So you have three colonies. Everybody's real-time clocks will be running at different speeds. Now, don't forget about the speed at which those planets or those heavenly bodies are orbiting, because they'll be orbiting at different speeds. So that means also time will speed up and slow down on those sites. Oh no, we have a discontinuity. So you're going to have somebody on the left here on Earth, and time goes on like this, but on the moon, time goes on like that. If you go over and you look at the Mars, time will be going on differently. Sorry, I'll go back to that. Time will be going on differently for them. So do we need a new standard of time? Now you see on the right-hand side here, we have the Greenwich meridian, where it starts the clock all the way around the, time evolution all the way around the Earth. And we also have a pretty good definition of what a second is. And so that way you can pretty well find out if it's, what is it? 1 o'clock, our meeting starts at 1 o'clock our time. It'll be starting at what, 4 o'clock or 5 o'clock? No, actually it's backwards. 8, 9, 10, 11, 12, 8 or 9 o'clock in the morning in Vancouver. So we can know that. But our unit of time on Earth ends up being meaningless on Moon or Mars. So do Earthlings need to set up a new time standard for interterrestrial time? Apparently, there's a lot of thinking that has to do on this topic, and our clock club needs to set up a special interest group to either design a new timepiece or, to set up a new timepiece, or to define a new standard of time that's appropriate for all scenarios. So there you go. There will be a call at the end of this meeting for that special interest group to come up with a new timepiece. But oh no, further on, this is where you get into being a real nerd. Further on in space, there are things like black holes. Now, if anybody watches Doctor Who, they go through wormholes all the time. His spaceship always goes through wormholes. Well, actually, what you're seeing here is an actual wormhole on the right-hand side caused by a black hole. So what is a black hole? A black hole is a huge, massive star that just keeps on sucking in because its gravity is so big. Things just keep on falling into its gravitational field, and it gets bigger and heavier and heavier and heavier. And finally, it's so heavy, it collapses in on itself to a very small, super duper high density star, planet. And the effect of that super massive gravitational fold is to warp time-space intensely. So you can see in this diagram, it can actually warp time-space, and you can go through the top, down at the bottom into a completely different dimension if you survive the trip. And so this is an example, a visual example of the warping of time-space because of a black hole. But at the top, let's say you're driving along that little lattice work thing, and you know, a minute is a minute. But as you go towards the center, time-space is stretched because of gravity so far that time virtually stops. So if you are in a spaceship where that arrow is pointing, basically there is no time. Time is basically stopped. So try to wrap that around your head. So the reason I'm only giving you this is to show you that, you know, on Earth we have a definition of time, and on all of our clocks work at different levels of accuracy based on time. But because we want to get off our planet and go to other places, we have to start thinking about all these extreme things that can happen. Here's another example of the black hole, where you chuck your clock into the black hole, and it falls down the hole, and that creates the wormhole. So that's where Doctor Who goes sucking through the wormhole into a different time period. And at the very in its most point there, or inner point, time stands still, or virtually still, depending on how far you go. How's that, eh? So why am I talking to you about this? What's the conclusion of all this? Well, the effect of time dilation, wherever you are on the Earth, is not perceivable. If you're on top of the CN Tower and somebody at the bottom of the CN Tower, nobody's going to notice the difference, but there is a difference. But local gravity and your speed can have an effect on space-time. If you're going to places like the moon or to Mars. Extreme effects of this are things like stopping time altogether, like with a black hole. So if humans plan on residing on the moon or on Mars, the implications of their local time could be quite disruptive. So you can see in the diagram here, somebody on the moon is saying, "I'll call you at noon for an hour," and then the person on the on Earth says, "Who's noon? And how long is an hour?" Because everybody's point of reference is different. So it's possible that at some point in the future, we're going to have to define a new standard of time based on space traveling to the moon and Mars, which we hadn't considered based on just living on Earth like we do right now. And that's the name of that tune. That article is in the newsletter, and then it's also on. It will be on the website. And if you like that sort of thing, join the coffee club meetings, and we can talk about that in the near future. Any questions?
Yeah, I have one. It's Clint Olton.
Yeah.
In a practical sense, can you hear me?
Yeah.
Oh, okay, great. If you're on this time continuum, does your hair slow down? It doesn't grow as fast?
Yes, absolutely. You are physically aging slower. So, you know, in movies, a really good example of this is in movies, some science fiction movies, they have shown somebody leaves, you know, an astronaut, maybe the Earth is ending, who knows what, but an astronaut leaves Earth and they travel really fast to Alpha Centauri, which is one of the galaxies closest to us. And then he speeds back again. And by the time he gets back, humanity has changed. Everybody he knew is dead. And they've aged maybe 5 centuries, where he maybe have aged a week. That actually would happen. So it's not, so that's not science fiction. That effect is true. So biologically, you would age more slowly, while everybody back on Earth would age the same rate.
But why? Where's the mechanics of it? Is your heart is going to slow down, or in other words, you have biodegradable things that are, you're shedding skin. You're what you're saying is that if you're in a spaceship and you're traveling, you won't have to have a haircut for maybe 2 or 3 months.
Or yes, or no. It's your month. So we're talking about relativity. And so I'm just going to move back to something here, a diagram that I had.
From your perspective, nothing will change.
There, I'm just going to share.
But if you're looking at you from inside the gravity well, or from outside the gravity well, it's almost like you're frozen. So if you want an example of this, check out the movie Interstellar. So they explore, in one part of the movie, they explore a planet that's next to a black hole. And so they leave one astronaut on the ship, and the rest of them go down and explore the planet. They explore the planet for maybe a few hours. Well, when they come back, the astronaut who they left in orbit is 20 years older. So for him, 20 years has passed. And for the ones who went down to the planet, only a couple of days have passed.
Yes, and the reason for this is I'm just going to try to scroll down. It's a bit clearer if you want to get your brain cells wrapped around this. There you go. It's this paragraph here. So look at the diagram, and the diagram shows that mesh work of space-time. And if you stay on the top of it, you know, all the mesh is consistent. It's basically space-time is consistent. But as you go down the tube, everything, this doesn't show it very well, but everything is stretched super long distance. So think of somebody traveling, or light. Okay, so sorry. The way they describe it is light. Light travels 300, it says it in the paragraph here on the left. Light travels 300,000 kilometers per second. Now, there's a distance there, kilometers, and there's a time unit there, seconds. So kilometers per second. If space-time is stretched out, the speed of light never changes. It's constant. It's one of those weird things that no matter what, the light of speed is constant. So if distance has increased because of the warping of time, the speed it's traveling, 300,000 kilometers, has to stay the same. So what has to change is the per second. So seconds slow down so that the light keeps up at same speed. So if you want to know the mechanics, that's the mechanics right there. Is that light travels at the same speed no matter where it is in the universe. And because we're talking about kilometers per second, if the kilometers increase because of that warping of the black hole in space, then to keep 300 kilometers per second, it has to slow down time to keep that speed the same. You just get the math. Just work it out on a piece of paper, and you'll see that space gets bigger. And so to keep up the same distance, you have to, there's only one other thing you can change, is that's the time. So you slow down time so that light maintains its same speed. So that's the actual mechanics. I'm sorry.
No, it's I'm familiar with all the concepts and the like. It's just that to get around the biology component of why your body has to still beat, has to create electricity, still has to shed skin, and what you're saying is that everything slows down. And are you aware of all these things that are being affected of your body?
Oh, and so this is where it's called the Einstein's theory of relativity. So it's your reference of your reference compared to somebody on Earth. And so if you and this is where I always get messed up. If you are the person going down the black hole, nothing seems different. Everything seems the same. You know, you're aging the same rate, but relative to somebody outside the hole, you've slowed down and aren't moving, and you're not aging at all. But the person outside is, and you're seeing them speed up. So from your reference point, they're speeding up and they're aging really quickly. But from their reference point, looking at you down that black hole, you stopped, because remember, time slows down to virtually stop. You stopped and you're not aging at all. And so for you, everything's normal, but you look outside the black hole and everything's speeding up.
Okay. Well,
freaky, eh?
I'm sure you have some more questions.
Hey, John, I have several clocks that might interest you, because they're permanently stopped, so they might be very suitable for your black hole.
I know some of my clocks run faster, some of them run slower. I think it's related. So there could be a black hole somewhere around you.